Using exponential forms of complex numbers can make it a lot easier for us to multiply and divide them together. So for instance, so we know that, let's say we have a complex number Z1 that is written as in exponential form as R1 times e to the I theta 1. And let's say that we have a second complex number Z2 that's written again as R2. Its modulus times e to the I theta 2. Any complex number we can write in this way. Well, if we want to form the product of these two numbers, Z1, Z2 is just, copy pasting everything, R1 e to the I theta 1 times R2 e to the I theta 2. When we can put the R1 and R2 together, and then we have e to the I theta 1 times e to the I theta 2. Brief pause here. How do we simplify e to the I theta 1 times e to the I theta 2? Well, exponents, when we have two things that are exponents multiply together, we add the corresponding exponents, and this just becomes e to the I theta 1 plus I theta 2, or e to the I theta 1 plus theta 2. And this is what we have for Z1, Z2, the product of two numbers written in the exponential form is just the product of their modulus, moduli, plural of modulus, moduli, times e to the I theta 1 plus theta 2. So just add those angles together. And similarly, if we want to do Z1 divided by Z2, then this would be R1 e to the I theta 1, all of that over R2 e to the I theta 2. So we can put the R1, R2 together. R1 over R2 will be the new modulus, e to the I theta 1 divided by e to the I theta 2. If we're dividing one power by another power, we subtract the exponents. So e to the I theta 1 minus theta 2. So these will be our formulas for how to multiply and divide together complex numbers in exponential form. And so as an example of this, let's suppose that Z1 is square root of 3 over 4 minus 1/4 I. And suppose that Z2 is 2 plus 2 square root 3i. And so what we're going to do is let's find Z1 times Z2. Let's do Z1 divided by Z2. And we want to do this using these exponential forms here that we just looked at. So to do this, what do we have to do? Well, we need to convert Z1 and Z2 to exponential form. So R1 will be the square root of 3 over 4 squared plus minus 1/4 squared. So that will be square root of 3/16 plus 1/16, square root of 4/16, 4/16 a quarter. R1 will be a half. And we also need theta 1 will be arctangent. The x here is positive, so we don't have to add pi. We can just say arctangent of minus y, of y over x. So arctangent of negative 1 over square root 3 is negative pi over 6. And then we also need to do R2 and theta 2 for Z2. So R2 is going to be square root of 2 squared plus 2 square root 3 squared. So that's going to be square root of 4 plus this right here will be 12. So that's going to be square root of 16 is 4, and theta 2. Again, x here is positive, so It's just, so theta 2 is going to be arctangent of y over x. So arctangent of 2 root 3 over 2. Arctangent of square root 3 is pi over 3. So what can we say at this point? Z1 is, we can write as R1 e to the I theta 1, negative I pi over 6. Z2 is 4 times e to the I pi over 3. And so to multiply these two together, Z1 times Z2 is just 1/2 times 4. All right, let's explicitly 1/2 times 4 e to the I. So theta 1 is negative pi over 6 plus theta 2 is pi over 3. And so this ends up as 2 e to the I pi over 6. And if we wanted to do Z1 divided by C2, so that would be so our formula here would be R1 divided by R2. So that would be 1/2 over 4, and e to the I theta 1 minus theta 2. So theta 1 was negative pi over 6, theta 2, so to subtract theta 2, pi over 3. So 1/2 divided by 4 is 1/8. Minus pi over 6 times minus pi over 3 is going to be negative I pi over 2. So yeah, this shows how we can use exponential form to have a slick way of multiplying and dividing complex numbers together. To kind of finish this off, let me just point out here that negative I pi over 2, that ends up being negative I when all is said and done. So this answer here is just negative I over 8. And I would suggest, it is maybe worthwhile go home and check for yourself that if you do straightforward division, Z1 divided by Z2 by the video stuff in the last video set, that you also check out as negative I over 8. For this one, 2 e to the I pi over 6, this ends up being 2 times, so e to the I pi over 6, cosine of pi over 6 is root 3 over 2, and sine of pi over 6 is 1/2. So this would be square root 3 plus I. Again, check for yourself that if you do Z1 times Z2 just straightforwardly, you end up with this answer. And this answer for Z1 divided by Z2. One last thing to stick in this video set to riff off of this, the idea of what's called de Moivre's formulas. So suppose that we have Z written in exponential form, R e to the I theta, and we want to raise Z to some power n. And this is going to be very critical in our next video about finding roots of complex numbers. So Z to the n would just be R e to the I theta, all of that to the n, which when we distribute it out would be R to the n, e to the I theta raised to the nth power. E to the I theta raised to the nth power is just e to the I n theta. So Z to the n is R to the n, e to the I n theta. If you want to raise it to a negative power, Z to the negative n, R to the negative n, e to the negative I n theta. So this allows us to do exponentiation very, 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 very quickly. So if I were to ask you, what is 1 plus I to the 16th power, let's say, what would we want to do here? We'd want to write Z is 1 plus I. If we write this in exponential form, You see the r is square root 2, and e to the I theta here would be pi over 4. So if we raise this to a high exponent, so z to the 16th, just for instance, would just be square root of 2 to the 16th e to the I pi over 4 times 16. And in fact, this simplifies down very greatly. Square root 2 to the 16th ends up being 2 to the 8th is 256. And this would be e to the I times 4 pi. And check for yourself, e to the I times 4 pi is going to be just 1. So this gives us a very quick way to see that if we raise 1 plus I to the 16th power, then we get 256, which might be a surprising answer. That, raising this number, there's i's in this, there's no i's in our final answer. So yeah, this will be very, very, very important in the next topic, roots of complex numbers.